Hello, today I am here with Propulse NTNU and we are here to discuss the latest project. So could you start by describing your new rocket?
We are now at the Propulse NTNU's test site in Trondheim. It's a new year, new project, and of course a new engine, more specifically a bipropellant liquid engine. So I don't know if you can see it behind us here, but there's a container which is containing our new engine for the rocket Heimdall. And with me now, Joachim, and he's the current chairman of the Propulse NTNU, the man who is leading the entire project, pretty much. So maybe we should mention a few words about the ongoing projects that we are working on these days.
Hello, my name is Joachim, and as Siemens said, I'm the current chairman of Propulse at our test site to test and validate our bipropellant rocket engine for the current project Heimdall. This is a rocket using ethanol and nitrous oxide, and it is a 5.8 meter long rocket which will launch from Norwegian soil. So we largely base this rocket on the previous 2 years of biliquid rockets we've made in Propulse, and with some new designs and ideas, and we plan to launch it from Norwegian soil during July this year.
Where exactly do you intend to launch?
So we're going to launch it from a small island called Tarva. This is a small island outside of Trondheim, where normally the military is practicing with their target practicing with their F-35s. But during summer, they have some spare time, so we can go out there and launch the rocket there.
How high do you intend to fly?
As of now, the target is right under 6 kilometers. Isn't the record for any propulsed rocket, but it's the highest we think we're going to target with this rocket this year, because we want to be as close as possible to guarantee a rocket launch.
Yeah, we, as you might remember, Etto, we built a rocket last year as well, where we pushed the limits quite a bit on both performance, but also like complexity in certain areas, and that doesn't go too well along with having a tight timeline and tight budget and all that stuff. So, so the new team is really focusing on reducing the technical risk of the project. Let's launch a rocket and focus and put our requirements alongside that goal.
So you're making still quite a big rocket at 5 meters. How much thrust do you intend to have?
The rocket will have a target thrust of 8 kilonewtons. Yeah, in many ways, as you say, it's quite large, and it's very big for targeting 6 kilometers of apogee. But as Siemens says, we want to make sure that everything has the lowest technical risk, and that means not weight optimizing and necessarily reducing all of the space and making it harder to work on and test.
This new engine that you are making runs on ethanol and nitrous oxide. Roughly what size is it, and what chamber pressure do you achieve?
It's largely based on the Bifrost motor, which launched with Bifrost 1.5 years ago. So the complete height of the motor is approximately 340 millimeters.
Somewhere along the lines of this, I think. Yeah, it's way back there in the container. You can probably send a picture or two afterwards.
Yeah, of course. The chamber itself is 3D printed in Inconel 625. And the injector is an impinging injector using aluminum. The target chamber pressure is at 20 bars this year.
What is the pressure of your fuel and oxidizer tanks?
The tanks will be at around 35 to 45 bars, depending on what the pressure losses will be when we actually get to hot fire the motor.
Roughly how much fuel and ISP do you wish to have?
We target at least an ISP of 180. We hope to get a little higher, but 180 is our goal. 33.5 kilograms of propellants, and we of course also, as you say, have a pressurized nitrogen tank of 250 bars.
How much will the entire rocket weigh?
The wet weight will be at 145 kilos, and without propellant it's 105 to 110 kilos, so it's quite heavy.
Compared to the solid rockets that we launched early in our careers, those were around 40 kilograms. 30 to 40 kilograms fully loaded with propellant. So they are quite different beasts from what we launched first time we attended EuRoC, but also over in Spaceport, America in 2022. These are huge rockets. The guys have already winded the airframe sections, and I got to see them yesterday, and like they are huge. It's almost like you could cram yourself together and crawl up there. And It's quite amazing to see the progress that, the scale that these rockets are progressing towards. But still, even at this scale, it's only 6,000 meters above ground, but it's still quite high if you think about over 100 kilograms of mass being transported.
How long have you been working on this rocket?
This rocket we started on in August, and we had the kickoff with all of the new members in September, which means that from September until now we have had to both learn, train the new members, and getting the initial concepts and design before we iterate and now test the rocket. So in total, from we start the project until the targeted launch, we would have worked on the rocket for 45 weeks. So it's not a long time, especially when we have quite some new concept combined with the previous knowledge we have from the previous two biliquid rockets.
You haven't been working very long, though. You have some experience from the previous, made of carbon fiber, I believe the airframe.
Yeah, most of it is. We also have some glass fiber parts of the airframe, since the carbon fiber is not radio transparent.
Yes.
So in order for us to have a good connection with the rocket, we have the forward airframe in glass fiber. That is the same we've had the previous years as well. And in general, we try to learn as much as possible from the previous years, and then iterate on that and continue to innovate on new ways to do things better, and have some areas of focus instead of trying to redesign everything every year.
I would like to also highlight another fact about this time frame and the team who is doing the work. When Project Valemon concluded last year, many of the board members and discipline leaders, they either started their internships like I did, or went on exchange years and such, meaning that there were a team of relative little experience members who were set to take over the lead for the new project. And Joachim, together with a lot of the guys and girls behind me now, they only worked at Propulse for 1 year prior to becoming the leaders of the entire organization. Another detail worth mentioning there is that they didn't even get to see a launch, because we didn't launch last year. So it's they've had to learn a lot in a short period of time, and they are doing quite a good job at it. So it's nice to see that the knowledge is actually being transferred, and they are being critical to what's been done before, and paving a new path. So I like to see that a lot.
Thanks.
And that's not given in these projects where new people take over every year.
The experience is very important in these rockets, as they are very complex things, and it's usually hard to find much information unless you know it by yourself.
Yeah, and at our university, there are no aerospace degrees. There are no fields of study that focus around rocketry or planes or anything. So all our members are completely fresh to rocketry when they join our organization. So that's also something that we are rather proud of, that we are able to achieve these quite complex and ambitious things based on the information that we find out ourselves through testing, or just by talking to experienced people around the globe.
What do most of the team members study at university?
Quite a lot of electrical engineering and cybernetics, and of course we also have a lot of mechanical engineers. Those are the main disciplines from university, but of course we have a lot of
Physicists.
Thank you. And from different economic studies as well, since our organization is not only the engineering, but it's also the non-technical disciplines, which makes the whole project a lot bigger and more similar in some ways to a normal company.
All the information required to build this rocket, you all found it from a bit of experience from last year's.
We've had of course, some great mentors, and last year there still was a lot of experience in the organization. Like Simon has been at Propulse for many years, and like him, a lot of other mentors that are still present in the organization to help. An amazing job helping both the current board and all of the members that currently work on the rocket to fast track the learning and increasing the understanding of what have been done before and what could be better. Additionally, we also have a lot of sponsors, which although they don't make biliquid rockets themselves, they still make quite a lot of very complex parts and systems, and they help with coursing and everything we need in order to have the best basis for designing and testing the rocket. But more than anything else, it's the previous years that have helped us be where we are now.
Compared to last year's design, what are the major changes in the biliquid rocket engine?
The most important one is that we've gone from liquid oxygen and back to nitrous oxide, like Bifrost. Last year's rocket used liquid oxygen, and we became quite good at hot firing the rocket with that combination of ethanol and LOX, to the point where we could do repeatedly the same test and get the same result. The main issue with liquid oxygen is that it's cryogenic, so it's very hard to store. To have that at test site here and test it when we were ready for a test is quite the challenge when we work on student hours. So that's the main difference. And of course, we also went back to an impinging injector instead of a swirl injector.
It's worth mentioning the fact about the LOX, which Joachim is mentioning. It's on paper, it's not necessarily hard, because you have these containers or dewars that is isolated such that the liquid oxygen doesn't boil off too fast. But that's only the case if this container is actually up to spec. And more often than not, they were not up to spec, meaning that it got delivered the afternoon of a Friday, and we started testing on a Saturday, and pretty much all of the LOX were gone. Yeah, so there were a lot of issues where we actually had a LOX container on site and we were ready to test, but we couldn't because there were no LOX left in the drawer, even though we haven't really used anything of it. And that's quite noteworthy of a logistical issue when you have to test for that weekend, but you can't because you don't have any LOX. And similarly with our launch site, it's rather remote, so it was not trivial to get the LOX dewar all the way out to where the launch rail was supposed to be located. So if there are any teams out there who are considering LOX versus N2O, LOX is nice for efficiency, but not so good for the logistics. Yeah. Because on paper it will be nice, but in reality it's not necessarily that nice. Yeah.
And especially when you work on the time frames we work on, 1 week doesn't sound like much, but it's one of only 45 weeks we have in total for the whole project, and one of maybe 5 or 6 weeks of testing. So then you lose 20% from that one dewar that leaks. So it's quite hard of a logistical challenge for a student project, at least.
But how can it be that the dewars are not as good as they're supposed to be? Do they get damaged, or?
So there were instances where the thermal jacket was damaged, meaning that the vacuum which insulates the internal jacket was not indeed a vacuum. It was ambient, so temperature just or heat was transferred rather quickly from ambient air into the LOX. But in general, they are put through the paces in industrial use, thrown around, and they are heavy duty equipment, so to speak. And also, it's not too common around here to use liquid oxygen for industrial purposes. There's a lot of oxygen that goes to these fish farms to aerate the fish containers that they use, but that's gaseous. So our supplier, they have a lot of experience on liquid oxygen worldwide, but locally here, it's not that common to use it. So they just have a small set of dewars that we had to choose from, and when several of them were damaged, there wasn't really too much to do about that.
What kind of efficiency gain can you get using liquid oxygen instead of nitrous oxide?
Quite a lot of difference. Of course, if you are looking at the ideal combustion, probably like tenths of seconds of specific impulse. Of course, we do not operate at the ideal mixture ratios due to thermal concerns and all that stuff. The efficiency gain is it varies on your setup. But the main reason for going with LOX, or there are mainly two reasons. It's the efficiency gain, meaning that you can bring less fuel for the same, or less oxidizer for the same apogee potential or impulse. And also it's industry relevant. If we, the members of Propulse, have experience working with liquid oxygen, which is the standard across the globe, really, for rockets, then that would be a added value from working on our projects.
So, of course, I mean, the main advantage of liquid oxygen is the experience you gain from using it.
At the end, that's pretty much what we got out of it. We got some experience working with it, which is rather rare, at least at our study or at our university. So that's pretty much what we got out of it. Of course, we got a launch from using nitrous oxide for Bifrost. So let's hope that's the result for the switch this year. That's not what we are what it all leans against, but it's it makes life easier.
Yes, it's also the nitrous oxide has many things which makes it easier than liquid oxygen. It's not cryogenic. It's also self-pressurizing, which is always useful for propellants. Almost it's easier to store and to find.
The storage part is pretty important, and also the size at which the containers come in. It's in a standard gas bottle, as with nitrogen and CO2 and all those other gases. So you don't need a forklift or a huge crane or something to move it around when you have acquired it, which is the case for the LOX. It's hundreds of kilograms for the LOX Tura.
It should be surprising that many teams have been able to use it, given all the challenges that.
It boils down to the Tura. If you have a well maintained and non-damaged Tura, the LOX will stay there for many days. But it's worth noting that I've seen some pictures of some US teams that use liquid oxygen. They have like 15 Juras on site or more. I don't know if they are brute forcing it with regards to the amount of LOX that they buy to counteract the defect rate of a Jura or the boil-off rate and all that stuff. But it's certain to say that they most likely wouldn't need 15 units of containers if they would have used nitrous oxide. But of course, it depends on the mission, the burn time, propellant mass flow, all that stuff.
We also wanted to use LOX for this year's rocket if it wasn't such a big challenge logistically. Since, as I said, at the end of the project last year, we got quite a good control of both filling and testing with the with LOX. So if it wasn't such a big challenge, or if we had better control over which Tura we got, or as Simon said, we had 15 of them, then we could easily have continued using LOX, because we solved what would normally be the direct technical challenges of using LOX in a rocket, maybe for next year.
Do you intend to go back to LOX?
There are some quite big advantages. So if the next year's board see it fitting, and it fits with both the timeline and the logistics can be a bit easier, then it makes sense to try to switch back, since we have some experience using LOX now. And if that is something that Pulse wants to go back to, then it makes sense to do it as quickly as possible in order to not lose that experience we currently have with using LOX in EuRoC.
Will you be going to EuRoC this year?
We decided against it, even though we had quite a lot of discussions internally, quite on the fence. But we want to increase the interest in space here in Norway, and we want to get some better connections here and develop possibilities of more rapid testing here in Norway as well. And when we had the opportunity to go to Tarva, the current launch site, that is a much more lucrative alternative for us at this point, especially since for us at least the project timeline fits better with a summer launch than in October as well. So we decided on a launch from Norway instead, because of partly that at least.
The Norwegian army or defense, whatever you classify it as, maybe it's Navy, I don't know. They are quite nice to work with. They find these projects rather cool, and they are able to reach out and help us more than we are used to. Really, like, they are very friendly, and they want to see this happening pretty much as we want. And they have a lot of facilities, workshops, camera surveillance equipment of our launch pad, a good connection with the airspace controllers, because this is close to an airbase where the F-35s of Norway are training every day. It's a good environment to be a rocket company that needs some help from external partners working from Tarva. But we of course see the benefits of EuRoC. I've been there twice. I've had great fun, and perhaps in the future, when we have enough resources, due to having more and more sponsors here in Norway, maybe we're able to send another team or a subdivision of Propulse to competitions like EuRoC, because they are a great experience to everyone. And then we can meet you and all the other teams as well. That's something that we will miss. But maybe when we get the hang of it, launching from Norway, it will be invites sent down to all the teams. And like, the airport is quite close to the airbase that we're launching from. The airport in Trondheim, it has direct flights to Munich and direct flights to probably Italy as well. I don't know, but it's quite accessible.
So you do not intend to go back to EuRoC in the near future?
Our plan is to continue on the main project, at least, to develop the connections here in Norway and continue to develop the possibilities of more tests. And focusing on that makes more sense, since it takes a lot of time and resources to design a rocket that fits in with the requirements of EuRoC. And even though we have it as a baseline for, since it's a very good, the EuRoC D-Tech is very good for good design practices. So we use that quite a lot. But in some places it doesn't fit as well with our rocket. For example, the total impulse for EuRoC is only 66% of what we have in our rocket currently. So as of now, it makes more sense to develop a rocket that fits in with a Norwegian launch pad, which we have more flexibility on.
Yeah, and also the altitudes might be quite looser when launching with the Norwegian partners. As you know, Etto, the ISAR Aerospace, they tried to launch from the Andøya Space Center up in the north of Norway. So the people working at Andøya is quite interested in the Norwegian student space scene. And of course, as we have tried every year, we have also this year tried to arrange for launch possibilities at Andøya, where ISAR is launching, showing to them that we are able to launch in a professional manner by ourselves, together with some Norwegian actors in Norway, will strengthen their faith in us to be able to launch from Andøya, which down the road could enable launches to 100 kilometers several times per year, or even higher. Like usually there are sounding rockets from Andøya that launch to 400 kilometers. Higher up than the International Space Station is orbiting from Andøya. So that's quite it has got some potential. We want to collaborate with these guys. Yeah.
Do you intend to go ever higher with the rockets?
Overarching goal of Propulse, in addition to, of course, being a learning platform and the stepping stone to space for students, aim to launch a rocket to space from Norwegian soil with a biliquid rocket engine. So that is one of the overarching goals, and that is easier to work towards while launching from Norwegian soil, since we have more flexibility, as Siemens said, both on timing and Apogee, and it can more easily be a test bed for technologies that are maybe not relevant for 3, 6, or 9 kilometers, but it is definitely relevant for a space shot in the future.
How high can you launch from your current launch site?
It's a bit hard to say. With the right conditions, I would imagine we can get close to 10 kilometers, but it depends. And
what does the airspace zone allow?
It allows for 8,200, but it can be increased with the right calculations, but the absolute maximum that is predefined for the area is 8.2 kilometers.
So that's the airspace that they are closing for the F-35 testing. So that's a huge benefit of this location, is that we don't have to apply to close the airspace. They already have this designated danger zone up to 8 kilometers that they regularly close down for these weekly F-35 tests. So last year, for our other launch location that we actually got a grant to launch from, which was further inwards in the country, we had to apply and follow some very strict requirements to actually get the permission to close off the airspace. So that's a hassle that we are relieved from doing at Tarva.
The rocket that you're currently designing will go to 6 kilometers. Why did you choose that as a target apogee?
Well, actually, this year we didn't have a target apogee at all. Our target was to have a higher apogee than the theoretical apogee of Bifrost, which was the rocket launched from EuRoC in 23. But our main goal was to launch, and that with a rocket that had the lowest possible technical risk, while still innovate on some key aspects that we had to innovate on and wanted to develop. So the apogee is more a result of having designs that make sense, are a bit easier to both test, manufacture, and assemble in the rocket to launch. So the apogee has changed quite a lot of times, but it's been a lot easier for us to not have to aim for a specific apogee, but focus on the actual both safety and technical risks of the systems.
What are these things which you innovated the most on?
Well, we have a completely new recovery system for one. So that is a system we haven't used before. When launching all of the rockets that we have launched have been based on a separation-based recovery system, where you separate the nose cone and then you have first the drogue chute before you then release the main chute. Change that to having a mortar-based system, which means that the drogue and main chute are completely separate, and you have a radial deployment of each one. This year we decided to use the drogue mortar, so we deploy the drogue chute radially from the rocket, And then we separate the nose cone for deploying the main chute and also inflating 3 flotation balloons. Since the rocket will land in water, we need to make sure that the rocket will actually float and will be visible from a boat in order to lift it up with a crane and get it back on land. In addition to this, we have a coaxial tank which is bolted. This is not necessarily because of the direct performance increases, but it's a product of reducing the technical risk, both in terms of the unknowns with the strength of the tank, but also the manufacturability of the tank is drastically easier than with a more weight optimized tank, which we had last year.
Yeah, I don't know if you remember from last year, Etto, but tanks were welded. One of the tanks ruptured at the welds during a hydrostatic test. So transferring it, or switching back to or over to bolted interfaces in the tank is to reduce the risk of relying on these welds in this highly optimized structure, which is the tanks. So, but I think the mortar system, that it was actually Joachim who designed that last year. It's quite a cool system. I haven't really seen too much of that in student rocketry before. It's 2 cannons which are mounted readily out of the airframe, meaning that you also have some huge holes gaping through the load-bearing outer structure of our rockets. As you know, with composite materials, having these holes greatly impairs their mechanical properties. It was a cool challenge. Number one, making these mortars and figuring out what pressures and what forces they will encounter, but also ensuring that the airframes actually are able to withstand the forces which it will be subjected to with these great holes. Like you could fit your head inside the main mortar hole. So that was a cool challenge. Unfortunately, it didn't fly, but precisely the same mortar for the Drogue is flying for this year. So we are not producing that again. We're reusing from last year.
Yeah, and that had some quite extreme performance as well. We only got to test the motors at ground level, but the ejection speed of the chute was at 100 kilometers an hour, and it accelerated from 0 to 100 kilometers in 0.01 seconds. So it was a very precise system, and we get to see this year how quickly it actually deploys the chute, but we hope we get a quicker opening of the chute as well from that, and thus reducing the speed the rocket will get from falling down from Apogee again.
What is the diameter of the airframe of the rocket?
Outer diameter is 245 millimeters. So it's quite big. It's 20% or so larger in diameter than Bifrost.
The mortar holes are very large.
In hindsight, the main chute probably shouldn't have been a mortar because of the like having a one cylinder normal to another is not very good if you want to have a small as small as a hole as possible in the airframe. So that is why this year we combine the both a separation and mortar-based recovery system. Then we get the ejection speed of a Drogue motor. We get the completely separated system, and thus have a increase in redundancy. But you also don't have to have a large hole in the airframe.
The whole airframe is wound out of carbon fiber.
It's a bit funny thing that we are winding it at the same facility each year, and we have done so since 2021. Become sort of this running gag that each time we're there, the guys get sick, but they still have to power through the production, because if they are not producing the airframes, we will not get any airframes, because it's a dedicated time slots where we have access to these guys' machines. It's formerly known as Winding Technologies here in Norway, but they are now called Spilka. And when I was there for biliquid, we were 3 people there, and 2 of us got COVID, but we still had to power through with the night shifts and shit food and all that stuff with COVID. So it was quite, it was an interesting experience. But we got to make some airframe sections, and the for Bifrost and for Valemon, the guys got sick. And for Heimdall now, which is the name of the current project, I don't know if we have revealed that name to some sort of sign that stuff is aligning well, and we're becoming more and more ready for launch.
So for the recovery system, these mortars, how are they made? Do they use like gunpowder charges to eject parachutes, CO2 cartridges? What do you use?
That is actually one of the main differences compared to a normal mortar system that you would see in a commercial rocket. This motor system is a cold gas system. We use pressurized nitrogen, which is fed into the back of a piston. And this piston will then be a part of the shock cord, in essence, pushing on the forward compartment with the chute, which will ensure that the shear screws or the pull brake screws of the lid on the outside of the airframe will pop off, and the chute will then follow out with the piston. One of the main issues with gunpowder is that it's not allowed for us to use here in Norway without specific licenses. So it was just a lot easier for us to design our own cold gas system, which we could test a lot easier. And since we already use nitrogen in the propulsion system, this was also easier for us to continue using.
An added benefit of having it being cold gas with nitrogen is that you get some relevant experience for what the people on the propulsion team are doing. So maybe next year you want to transfer to the propulsion group with some relevant experience working with piping and pressurized systems.
Yeah, we actually had we were 3 on the recovery system last year, and the other 2 are now in the propulsion discipline. One in feed system and one designed the current injector. So there's absolutely a relevancy there.
Does the rocket have some kind of steering system, or do you only have fins to keep it straight?
We only have fins. We don't have any thrust vectoring control of the rocket, so we need to have a thrust-to-weight ratio. This year it's at 5, so that means that the fins needs to be very large as well in order to have the stability. The rocket will launch from a 50-meter long launch rail, which is just 2.5 times as high as the rocket itself is, which means that it needs to accelerate to 100 kilometers an hour in 1 times the length of the rocket. So it's quite a big challenge and one of the biggest constraints on the total apogee of the rocket, since you need to reduce the wet weight of the rocket in order to have necessary stability.
Could you not have made that taller launch rail? Is there a limit to the size?
You can, in theory, increase it, but at some point it becomes very hard to make it stable enough. Our launch rail is designed in a way that makes it safe to have set up to a storm. Since we're setting it up at on an island quite far out into the ocean, it would become unstable at a certain point, and we want to ensure that it is stable and we can have it lifted up in advance of an actual launch, so we don't need to be dependent on first lifting the rocket and then launching it. But in general, at some point as well, you need to have more beefy trusses, which are the elements that put together the launch rail. So it's also just a constraint on what we have available.
One of the things that we have been wanting to do these past projects is to have liquid rockets that are capable of flying with the EuRoC supplied rails at EuRoC. So you might remember that Bifrost, it used I believe it was 12-meter long launch rails that EuRoC supplied, meaning that we only had to focus on bringing our rocket down there and preparing that instead of also having to prepare a launch rail. Of course, having it launch from the same rails as these solid rockets with thrust to weight of 10, 15 or above is, might say, an unnecessary challenge, but it's been a very nice engineering challenge for us to make a lean rocket that performs as good as a solid would with regards to the requirements put forth from the rails. So last year's rail was 12 meters, I believe, even though we made it ourselves, just to challenge ourselves and also potentially have EuRoC as a backup launch opportunity. But things are looking good for launching here in Norway, so why not have it be 15 meters and we can focus on other aspects of the rocket as well.
Yeah, that is one of, as well, comes back to the main focus of the project, which is to launch. So if we ended up in June with a rocket that needed 3 meters more and we didn't have it available, that would be a very sad reason to not launch. But still, 15 is, as it looks now, probably a bit more than we actually need as well. But it's nice to have that buffer for this year at least.
So in the coming years, you wish to reduce the necessary height of the rail. So you want to increase the TWR even more so that it will be possible to launch with the EuRoC rails.
I think at some point it doesn't really make sense to try to reduce the height again, since it looks more and more likely that we won't go back to EuRoC with a liquid rocket of this size. Therefore, as of now, I can't speak on behalf of the next board, of course, but it seems more likely that we would try to increase the or make the rocket more lean, and or maybe try to develop a TVC system which would reduce the actual need of a long launch rail in order to have the mechanical stability of the passive stability of the rocket, and instead controlling it actively.
So thrust vectoring could be the solution, and it's not a restriction due to us not being a part of a competition as well.
Though I assume that using thrust vectoring would be much more complicated.
It adds to the challenge of building a rocket. So that's something for a coming project to delve into. But one could do a safeguard in having it such that the rocket would be. It has a rail that is long enough to allow for the rocket to be passively stable with the TVC disabled in case it's not ready for the launch window. And maybe the year after that, when you've gotten an additional year to iron things out, you reduce the length of the rail again and actually utilize the TVC capabilities.
Yeah, I think also at some point it's nice to remember that we are a student organization. So even just making a liquid rocket in and of itself to fly 6 kilometers isn't in general the most efficient way of doing it. But because of us being students and we want to learn more than anything else, we take on challenges that are harder and not necessarily viable. But in order to increase the learning opportunities for Propulse and the students, we can afford to make some more fun choices that are harder, but also increases the learning output of the organization. And thrust vectoring could be one of those ways. We already did it with a liquid rocket.
Do you think it would be better to use thrust vectoring or to use rotate the fins? I'm not sure, I don't remember the right term for it, but to use the fins to steer instead of thrust vectoring.
Do you hear the drone that is flying above us, Etto?
A bit.
Yeah, they are flying away now. Yeah.
You can do both. Both works, but the way I see it, stabilizing the rocket using fin actuation is a bit harder because the period of flight that you need this actuation the most is the time period that you have the least control authority. So when you are on the initial acceleration of the rocket, you need a lot of stabilization, but you also have almost no air flowing on the fins, and thus you don't really have a real control authority. While with thrust vectoring of the motor itself, you of course have a lot more control authority since you have the thrust of the actual rocket to steer the path of the rocket.
What is, your timeline kind of for the next years? When do you intend to try to add new things such as thrust vectoring, very roughly?
As of now, we still are on a 1 year 1 year per project or per rocket, and that of course reduces the amount of things you can do within a year, but it also ensures that you can take some new challenges on when you start a new project. And we also have our side project called Hoppen, which is a hopper that is a basis for tuning our algorithms for thrust vectoring at some point. So as of now, it's more of a side project, but at some point maybe it would be viable to introduce into the main rocket, as Simon said. Maybe you can put it in there, test it during hot fires and not launching with it active. And this is also something we're looking into for, and one of the reasons why we want to pivot towards launching from Norway, since it's easier for us to do some low Apogee tests of systems that we are maybe unsure of or still develop, rather than going to a competition launching once a year and then you need to test everything on that singular flight.
I'll just break in and say that this is a sign that a test is most likely around the corner, because these guys aren't just here for enjoying the sun, they're actually working and preparing a test. I do believe that a test is imminent, so I suggest that we can round off at this point, and we will be sure to send some footage of whatever is happening at the test stand when the timer hits 0, so that maybe you can implement that to the episode. What do you think?
That sounds good. And then I shall leave you to your testing.
Thanks a lot. It was nice talking to you, Etto, and we'll be sure to keep you and everyone else posted. And thanks a lot for taking time off during Easter to talk to us. We really appreciate it.
Yeah, it was very nice to talk to you, Etto. A lot of people have talked about you and are really amazed of your interest in rocketry in general. I haven't, of course, met you in person, but the people that have really think what you do is quite amazing.
Thank you. Okay.
Bye. See you.
Happy Easter.
Thanks.
Happy Easter.
You too. Bye-bye.
Bye.
Bye.